You point a powerful GPU at a local AI model, and it still answers word by painful word. The math isn't the problem, it's waiting. The only question is, waiting for what? I was running a local AI model on my laptop, LM Studio, a medium-sized task. It was slow. My first thought, I need more RAM, but when I checked, my RAM wasn't even close to full. Something else was the bottleneck, and it took me a while to realize what. It wasn't about how much memory I had, it was about how fast the chip could actually read from it. Once that clicked, I understood why my setup was struggling. And it's the same reason your setup might be too. Let me show you. Every stick of memory advertises two numbers, and most of us watch the wrong one. The first is capacity, how much it holds in gigabytes. The second is bandwidth, how many bytes it can move in and out each second in gigabytes per second. Capacity is the size of a warehouse, how much you can store. Bandwidth is how wide its loading dock is, how much you can move through the door every second. For most of computing, capacity was the number that mattered. For AI, it's bandwidth, and that one switch explains almost everything that feels wrong about running a model at home. Here's what a model does when it answers. The behavior, it writes one token, roughly a word piece, at a time, one prompt at a time. The mechanism, a model is billions of trained numbers called weights, and to produce each single token, the chip reads every one of them, start to finish. An 8 billion parameter model in half precision is about 16 gigabytes. The consequence, it streams 16 gigabytes out of memory to make one word piece, then does the whole thing again for the next one. That gives you a ceiling you can almost do in your head. Tokens per second tops out near the memory's bandwidth divided by the model's size. Take an RTX 4090, about a terabyte per second, 1008 gigabytes to be exact. Stream a 16 gigabyte model through it, and you top out around 60 tokens a second. A theoretical ceiling. In practice, you get less. And the mechanism behind the feeling, at batch 1, the 4090's math units can multiply far faster than memory can deliver weights, so they sit mostly idle. Engineers call this memory bound. Throughput is capped by bandwidth, not by compute. Your expensive chip isn't working hard, it's standing at the dock, waiting for the next delivery. Because capacity and bandwidth are different levers. Behavior, add more RAM and decode speed barely changes. Offload a model into system RAM and it can crawl. Mechanism, capacity only has to clear one bar, the model has to fit. Past that, extra gigabytes just sit there. They don't move bytes any faster. And your system's DDR5 is a far narrower pipe than the GPU's own memory. An RTX 4090 moves about 1008 gigabytes a second. Dual-channel DDR5, roughly 77, about 13 times less bandwidth. Trade-off, spilling weights into system RAM to make a model fit buys you capacity and pays in throughput. Offloading is typically 1 to 2 orders of magnitude slower. Consequence, nothing changed but the width of the pipe. Engineers widened it. The answer is HBM, high bandwidth memory, and the mechanism is width first and foremost. Ordinary RAM talks to its chips over a narrow channel. HBM stacks memory dies into a tower and exposes an enormously wide interface. 1024 bits per stack, several stacks per accelerator. A wider interface moves far more bytes on every clock cycle. More bytes per clock means the GPU spends less time waiting for weights. Less waiting means token throughput climbs. That's how a data center chip reaches 3.35 terabytes per second on an H100, 4.8 on an H200, and up to 8 on a Blackwell B200, thousands of times a laptop's memory. Underneath, it's the same physics as any DRAM. Every bit is a speck of charge on a microscopic capacitor, billions of them, each slowly leaking and needing constant topping up. HBM just reads a vast number of them in parallel. The win is the width, not raw per-pin speed, and not merely sitting close to the die. That race has a name and a date. In 1995, Wolf and McKee called it the memory wall. Compute and memory bandwidth both improve as exponentials, with different exponents. Put real numbers on it, from Golami's 2024 analysis. Peak compute roughly tripled every 2 years. DRAM bandwidth scaled only about 1.6 times, and the links between chips just 1.4. Behavior. Every generation, compute pulls further ahead of the memory feeding it. Mechanism. That's why the industry now spends fortunes stacking memory and widening buses instead of only adding cores. Trade-off. At scale, you can hide some of this by batching. Serving many prompts at once reuses each wait read and puts those idle math units back to work. But for one prompt at a time, and for long contexts, bandwidth still rules. Consequence, shrinking transistors further, the 2-nanometer race everyone talks about, mostly buys cheaper compute you often can't feed. We keep building faster engines and forgetting to widen the road. An AI model writes one token at a time, and at batch 1 it must stream every weight out of memory to make each one. So decode speed is set by bandwidth. The bytes per second you can move, not capacity, the gigabytes you can store. Adding RAM only helps until the model fits. Past that, only a wider, faster memory interface, like HBM's 1024-bit bus, raises throughput, which is why AI chips stack memory instead of hoarding it. And because compute keeps outrunning bandwidth, about 3-to-1 every 2 years, that memory interface is the wall the whole field is now building against. Which raises a stranger question. If shrinking transistors just hands us compute we can't feed, what does 2 nanometers actually buy us? And is it even 2 nanometers? That's next.